how we always think about it. There's also really more to it than thinking about the gravitons or downstate of gluons. I mean, we still don't know maybe the right way to think about this, but it's there to have more than one way. But essentially, I want to stand on this strong coupling condition, because it's really, as I said earlier, more than this. Now after last lecture discussion, I can say really what I mean by strong coupling. So in terms of decreasing length, the picture one has is that there's the ADS scale, and the string scale, and the Planck scale. There are M-theory duals where the string theory has merged into the Planck scale. There's only one scale up there. But the main thing is that there's this big, that I emphasized from the start, is that there's this big separation. And so the states you're seeing down here are only the mass, they can only involve the massless string states, the supergravity states. And so in particular they have spins less than or equal to 2. So in this framework, so given the discussion last time about the relation between the mass of the states and their dimensions, it means that in this framework, operators of spin greater than or equal to get large dimensions. And if you look at canonical dimensions, if you look at canonical dimensions, you can easily make spin 3, spin 4 operators have a couple fields and a few derivatives, which have small canonical dimensions. So that means in particular there are large anomalous, really large anomalous dimensions. And this implies strong coupling. Very strong coupling, much greater than 1. So, of course, so it's not really true that the arrow of inference runs the other way, that very, very strong coupling implies large anomalous dimensions. And so I guess I should say, the more precise condition is this. And so not every theory which seems to have very strong coupling will be very strongly coupled in a narrower sense. This is the precise condition. Now, there are theories, there are these Basilian theories which have infinite families of higher spins, and it's not clear how they fit into the picture. In what sense, are those, in some sense, the Basilian seems to be shooting for a theory which is not all a string theory, and yet which has the power of higher spins. And I can't tell you how this fits into string theory or into ADS-CF duality, but certainly in this kind of framework where it's a normal low-energy effective field theory, it's a narrower condition. This is the condition that has to hold. And again, the conjecture that I'd like to make is that this is actually a sufficient condition. And they said, and others have made some progress in proving that by looking at smaller systems to have only a few operators, showing that in this case, you can from this condition derive the existence of a gravity dual. Anyway, so good. So this is the real condition. The real condition when you satisfy something like this. Now I want to return to unless there's, I'm sure there's more questions at some point, but now I want to return to the main theme, which is to start just again to continue with the duality dictionary. And I want to start with impersonal Eve, which is that one sometimes hears this mythical statement that the duality is really sort of most naturally formulated as the Euclidean thing, and then the Lorentzian thing is kind of derived from public quotation. I don't know if any of you believe that. I think I've heard it a few times and it always bothers me. So that's why I've emphasized that I think the basic statement of duality is this. Between operators in the CFT and operators in whatever those are. And the point again is that the quantized part of this operator, the quantized part of this operator has the behavior due to the delta, and so cancel that off and has a smooth limit and defines an operator in the CFT. And the dictionary often starts with some statement about generating functionals, and this is equivalent to that, as we'll derive today. But I like this one in particular. Well, so this statement as made is neither Lorentzian or Euclidean. Whatever signature, you can take, it works in both signatures and it's true in both signatures. Only, when we bring back a step when you're observable to the state, when we say that the duality is a one-for-one mapping of the eigenvalues of the Hamiltonian, that statement is neither Euclidean nor Lorentzian. That's a statement at some single time, and the difference between Euclidean and Lorentzian is just whether we revolve forward in time with either the minus ht or with either the minus iht. So it's really just that statement is timeless, and then you build an Euclidean or Lorentzian geometry by evolving from it. Okay, end of that piece. But I'll do the first calculation simultaneously in the Minkowski and Lorentzian signatures. So now, the simple thing to ask about is the two-point function. And as I mentioned earlier, of course, this is only constrained by symmetry except for its normalization, but is a good warm-up for things that have more physics in them. And so according to the dictionary, this is the limit of a Hall propagator. And this is something one can calculate. Actually, let me So this is just a Klein-Gordon propagator from massive field, the ADS base. I'm not going to write it all out because it's a hypergeometric function, but this thing is, call it G sub delta of C. So there are 2 points in the bulk of ADS space, and there's a single, there's a sort of the distance between them, maybe the length of the shortest distance between them, and that's all the propagator can depend on. And that distance is a function of this combination, I get Z prime over Z squared plus C prime squared plus X minus X prime squared. Just make sure we get, for some reason, is a form of the full hypergeometric form of this thing, and I've mentioned several times if you go to Eric Doker's TASI lectures for details. But anyway, this is what's looking at. And now again, this so far it all works in either Euclidean or Lorentzian signature. So to continue that point, in Euclidean signature, what I mean is that X minus X prime squared is the sum over Euclidean directions I equals 1 to D X I minus X I prime squared. And in Lorentzian signature, this would be instead the sum from I equals 1 to D minus 1 xi minus x prime I squared, and then plus I plus epsilon squared xi naught minus xi naught prime, naught. So this is just what you get from this if you rotate back to the Lorentzian time axis. And I'm doing everything here in terms of Poincare time, and you can also, it all makes sense. So everything here is in the Poincare coordinates again because those are the natural ones for the applications. So all I'm trying to get from here to here is to rotate 90 degrees in the complex plane, actually 90 minus epsilon degrees, because that's how you get the time order Lorentzian correlates from the complicated ones. Anyway, so if you solve the Klein-Gordon equation, in this form, and the only thing that we need to know about G sub delta, two things. First of all, this C, the way it's been defined, well, you can see that it goes to 0 for separated points, for x not equal to x prime, it goes to 0 as we take the points to the boundary, and G sub delta just then goes to, as you might guess, C to the delta, which gives phi the right boundary condition. And there's some more constants, which I'm going to ask you right now. I'm going to put all the, I think it was Mario who mentioned that I like to get all the constants right in my equations. I don't actually like to, it's simply a compulsion. And it's not always a compulsion, but every once in a while it seizes hold of me. And in this case I'm going to try to do it. So in particular it goes to something called C sub delta over 2 delta minus C. So for the next, I don't know how long, half a lecture, I'm actually going to keep a bunch of constants. Partly because they're sometimes gotten wrong. John McGreevy does this calculation in 3 different ways, and the answer, it gets one answer twice and the third answer once. And so by majority vote, he takes the answer he gets twice. And this is, anyway, I'm doing it partly because it's possible to get the wrong answer. And actually, when you're comparing these 2-point functions with observation, there's a meaning to the normalization. And so why not? But I want to understand, why people get different answers. Okay, so anyway, and this C delta is I need to find some solution to this problem. Having made notes on the computer, I need to get a real idea. Okay, so far it's just solving the Klein-Gordon equation. You solve the Klein-Gordon equation, you get about the constant. But anyway, the main thing for the present purposes is you go to the boundary, you get this funny coordinate C and delta, and that's just right to give this a non-zero limit. You can now take the sorry. Since I want to there's a standard convention in this field, and this is not it. So I'm going to put another normalization constant C sub O into there, and later on tell you what the standard convention is for C sub O. Okay, and so when you combine that with that, the 2-point function, so you plug this in there.